Thanks for coming. So today we have Siggers from Kyungpook National University. Surprisingly, this is first time for him to visit, I guess. Very pleased to have him here. We talk about I guess dichotomy, right?
Yep. Exactly. Yeah. Okay. Okay. Well, thank you for the invitation. I'm glad I could finally make it up here. Right. So what we're going to talk about, exactly. We're working on a complexity classification for a certain problem, and the work I do is with my student Hyobin Kim, but I'll also talk about some work of some other researchers. Okay. So let's start with the definitions that we need. So we're going to be talking about signed graphs. So what's a signed graph? It's just a graph, but every edge has a sign plus or minus. Right? So these were introduced by Harari in about 55. It's generally accepted that. And there's various applications of them. There's a fair number of papers on them. We're not going to get into any of the applications, but I want to introduce a couple concepts related to signed graphs. And the first one is that of a balanced cycle. So a cycle in a signed graph is balanced if it has an even number of minus signs. Right? The idea is that they multiply all the signs around the cycle, and if it's positive, it's balanced. And then another notion that comes up in a lot of papers about signed graphs is the notion of switching. Right? So a switch of a signed graph is we take a cut set of edges and complement the signs on that cut set of edges. Right? So alternately, you can say we switch on all the edges adjacent to a single vertex, and this defines an equivalence class of graphs that you can get between with switches. And generally, questions about signed graphs, we talk about the class, the switch equivalent graphs. Okay, so this switching plays well with the notion of balance of cycles, because when you switch, balance is preserved on cycles. And so we need one result, a result of Zalewski from 82, and he said in a bipartite signed graph, we call a graph balanced if we can switch the whole graph to positive. And he said in a bipartite signed graph, a bipartite signed graph is balanced if and only if, it's balanced if all cycles are balanced. Right, so we say a graph is balanced if all cycles are balanced, and Zalewski showed us that it is balanced if and only if it's switch equivalent to a graph with all positive edges. So we'll need that later, but that's enough for sign graphs now. So the plus and minus have interpretations. They have uses in a lot of the applications, but they don't for us. So we're just going to replace them with colors. And we're going to talk now about a red-blue graph. Right? And because we care about CSP and it makes things more interesting, well, we're going to allow loops. And we're going to allow an edge to be red and blue at the same time. Right? And so if it's red and blue, I'm going to draw it as purple. Because, yeah, I guess you know why. Right. Red and blue make purple. Even my daughter could answer that one. Okay, so, right, this is enough about signed graphs. Now, with graphs, we can always talk about a homomorphism. A homomorphism of two graphs is a vertex map that preserves edges. And why do we consider homomorphisms? Somehow you take a graph to a simpler graph and preserve some of the properties of the graph. So we want to do this with signed graphs as well, but we're interested in the switch classes of the graphs, and homomorphisms don't necessarily preserve that. Right? So we can certainly define a homomorphism of red-blue graphs that simply preserves red edges and blue edges, but we want this to work well with switches. So Nazaraza, Rolova, and Sopina, they defined a switch homomorphism. So a switch homomorphism from a signed graph G to a signed graph H is a homomorphism from something that's switch equivalent to G to H, right? So to get a switch homomorphism, we switch and then take a homomorphism. Right? So they defined this as a switch homomorphism, and then once they've defined this homomorphism, Well, they can define the problem, switch hom H, which asks for a given red-blue graph, is there a switch homomorphism to H? Right? So this is a computational, this is a decision problem. And so it has some complexity, some running time. Sometimes it's going to be hard, sometimes it's going to be easy. Right? And so they ask, well, what is that computational complexity? They asked that, and we answered that. So Brewster, Foucault, Helen, Mazarazer, they attacked it first, and they got the characterization of the easy problems while they conjectured it. Right? So they said it's polynomial time solvable if the switch core, and I'll define that in a second, has at most 2 edges and is otherwise NP complete. So they conjectured a dichotomy. They did a lot of work towards this. So for all the things they conjectured were in P, they showed it was in P. And for most of the things they conjectured was NP complete, they showed they were it was NP complete. They left a couple cases, and showing things hard is kind of showing things is hard is my bread and butter. So with Brewster, we finished that off pretty quick. And so what is this switch core? Well, it's sort of homomorphism lore, right? So for when you have a graph H, you can take homomorphisms of that graph to subgraphs, right? So the core of the graph is the smallest subgraph to which the graph admits a homomorphism, right? And so why are we interested in those? Well, we're interested in deciding if a graph G maps to H. But since H and its core are homomorphism equivalent, it's enough to ask if G maps to the core of H. Right? And the core of H is smaller, and it's a little bit more rigid. It doesn't fold as much. So it tends to be easier to answer these questions. It has some nice properties that the general graph doesn't have. Yep. The core is unique up to isomorphism. Yeah. Yeah, categorically, you can show that without too much work. It's not too bad. Right, and so actually everything I said about that is quite categorical. So we do it for homomorphisms, but we can also do it for switch homomorphisms. The same thing holds. And so if it's the core with respect to switch homomorphisms, we call it the switch core. And so that's what this switch core is. Okay. Okay, so we showed that, and then Pavel, he asked, well, what about list hom? Right, so we can ask the same question, the switch homomorphism, but we can ask a list version of it, right? So for every vertex in the instance, we give a list of possible targets in the target. Right? And so, yeah, what about list hom? Well, I didn't care about list hom. So what about list hom? What I know is that if something is hard, the homomorphism version is hard, well, then I can just take instances where every list is full, has all possible targets, and so list is hard. Right? So if the hom problem is hard, the list hom problem is hard. And so there's not many cases we have to deal with. Right? So is that what's left? We have to look at targets with at most 2 edges and decide, is it easy when we do a list version, or does it become hard? Well, actually, that's not all we have to do, because the notion of switch core changes when you look at list homomorphisms. When we're playing with list homomorphisms, every graph is a core. Huh? Yeah, okay, so I have to explain that. So I want to talk a little bit about relational structures and CSP in general, give you some background, to explain why this is different, and to explain why this theorem and this question are maybe interesting, why we care about it. So what's a relational structure? It's a generalization of a graph, or maybe a generalization of a digraph. So we start with vertices, and then we have a whole bunch of relations on those vertices, a finite number of finitary relations on those vertices. So we can have a binary relation. It's directed, it's not a graph, it's a digraph. So we can have a binary relation, but we can also add another binary relation. A relational structure can have many relations. We can look at unary relations, right? And these are the ones we're mostly interested in this talk, but of course we could have ternary relations. I draw them as circles, but they're directed still. And so this is what a relational structure is. And so we can define these relational structures. And then we define homomorphisms of relational structures in the obvious way. That's a map of vertices to vertices that preserves the red edges, and preserves the yellow circles, and preserves the orange potatoes? Potatoes. Okay, so for every target then, for every relational structure, we define the homomorphism problem, the decision problem, whether an instance has a homomorphism to that, and we call that CSP for the target. So this is H, and we call that problem CSPH. Right. And this is quite an expressive language, right? These CSP problems, we can express a lot of problems in that. In particular, yeah, we can express the graph homomorphism problem, even for symmetric graphs, right? So if I want to decide if there's a homomorphism to a symmetric graph, well, I'm going to use the relational structure with one binary relation, but I'm going to make sure that relation is symmetric, right? It goes in both directions. So in my instances, I only need one. I only need one direction, but it can, if I'm mapping an edge to an edge, it can go either way because I've made my target symmetric. Right? So yeah, CS graph homomorphism is the same as a CSP problem. And graph retraction or pre-coloring extension is also an instance of CSP, or it can also be encoded into CSP. So for that, we put these unary relations, a single unary relation on each vertex of a different color. And so now if I want to map an instance, in an instance, if I put a green circle on a vertex, that says, well, it has to map to here. Right? So we can pre-color some vertices and then ask, is there now a homomorphism that extends this pre-coloring? So that's, and so this is equivalent to the problem of graph retraction. And, well, graph list coloring is also a CSP. So actually, we can encode that. Notice if we have these three circles here, that one vertex with the green circle has to map to one of these. So in a way, we're defining a list where that vertex has to map. Right? So if we want to make a list version of a problem, I have to put in all possible unary relations. Right? So for every subset of the vertices, I add the unary relation where the singleton in that subset is in the relation. Right? And so I can assign lists in CSP. And right, so we have homomorphism, retraction, list coloring, and we can do this for all sorts of structures, right? For hypergraphs, for two edge-colored graphs, which we're interested in, and so on. Okay, now we've defined what a CSP is. People have been trying to prove this, for some 20 years, and finally Bulatov and Zook said, well, for any relational structure H, the CSP problem is either NP, is polynomial time solvable, or is NP complete. Right? So there's a dichotomy. It's either easy or hard, and it's not in between. Right? So if P is not equal to NP, we expect things to fall in between. But they said, no, it's either here or here, P or NP. So this is called a dichotomy. And so not only did they say there is a dichotomy, they told us what the dichotomy was. The easy H, we get an easy problem when the core of H admits what's called an WNU polymorphism. Okay, so what's a WNU polymorphism? Here's the definition. So it's a homomorphism from a kth, this can be any k, a kth categorical product of the structure down to the structure itself that satisfies this identity. So what's this identity? It just says if most, right, so it's a mapping. So here, what are these? These are all vertices of H, and I'm mapping them to another vertex of H. Right? And so this identity says if all but one of the vertices is X, all but one of the vertices is the same, I can mix up the order of the entries. Right? And so I don't want to define this product. It's the categorical product. But what does it mean that that's a homomorphism? Well, with an example. So say I want to define a homomorphism on this graph, right? A polymorphism on this graph. So a mapping from the third product of this graph down to itself. So I take 3 entries, and I have to map them to some vertex. Right? So say I map them to this vertex. To say that this is a polymorphism, well, when I take adjacent vertices, for each of these I take an adjacent vertex, well, then that has to map to a vertex that's adjacent to this. Right? So that's all it means that this is a polymorphism. A very natural definition. K is 3 here. Sorry. Yeah. So when K was 3, so I'm taking a map with 3 vertices for every triple of vertices, ordered triple of vertices, I map to a single vertex. Yeah, there's 3 circles there. 3 red circles.
Did you go back to the previous one? Restrictions versus just
Right. So all but one of the entries is X, and I'm just moving the Y to any place.
I see. That constant.
And the image stays the same. Exactly. Yeah.
This is okay. So if you
Right. So as long as there is a homomorphism for some K, I think it has to be greater than 2. Yeah, that seems, it must be at least 2. If we take up, yeah, it's weak near unanimity. So if you take off the W, if you put an X here, that's actually called near unanimity. Right? So if almost all the entries are the same, all but one of the entries are the same, then the image must be that entry. So that's called a near unanimity polymorphism. And the W means, well, we know they're the same, but we don't know where they map. Yeah. Okay, so it's a mysterious thing. I hope you say it's mysterious. So there's some obvious questions. You ask, well, how does that make the CSP problem easy? And what structures have that? Right? So the theorem leaves a little bit to be desired. Well, okay, as to the question of how it makes it easy, well, we've got to read their paper. So Bulatov and Zuk, they say, if I have a WNU polymorphism, then here's the algorithm to decide if a guy maps to me. And so I'll give you a feel for how that works with an easier. What? Oh, a different version of the page changed. Okay. Right. So there's these 2 obvious questions. And so how does it make CSP easy? Well, I can explain it. My colors are gone. Oh. Okay. So you can't see what's written here. So this is the egg of weak near unanimity graphs that admit weak near unanimity polymorphisms, right? Or the kind of weak near unanimity polymorphisms. And there's stronger versions. There's near unanimity polymorphisms. There's maybe semi-lattice polymorphisms, polymorphisms. And each of these guys, if a graph or a structure has these, we have a pretty easy polynomial time algorithm for deciding if something maps to them. And so if they have this other property that they're conservative, well, this is what we get with the list problem. So we'll talk about that in a second. But so when we're dealing with the list problem, all our polymorphisms have this property that the image must be one of the original entries, simply because of all these unary relations. But anyways, right, so, okay. So in here, somehow, when we have conservative semi-lattice polymorphisms, there's something called a min polymorphism. So it's a very strong weak near unanimity polymorphism. And so here's how I would decide a list problem if I have a minimum min homomorphism on my target. So there's a simple decision. There's a simple algorithm for kind of deciding if there is a homomorphism from a list homomorphism from one structure to the other. Every vertex has a list of possible targets. And so you take 2 adjacent vertices, and you look in this list, and maybe there's some A in that list. Well, if this guy doesn't have a neighbor of A in his list, this guy can't map to A. So I'm going to take A out of his list. Right? This is called consistency check. And so we just keep doing this and keep doing this. And if one of those lists becomes empty, there's no target for that vertex, and there can be no homomorphism. Now, in general, if you do this consistency check and you're left with non-empty lists, you only know there might be a homomorphism. But if the target has this min polymorphism, then you use that min polymorphism, and for each list, you just choose the min. It's a min ordering of the vertices. You just take the minimum vertex in its bag, and that will be the homomorphism. So, right, if you have this min ordering of the vertices, this min homomorphism, list coloring is easy. Okay, yeah, the algorithms get difficult for the different polymorphisms, but it works.
What's the property of the ordering?
What's the property of the ordering? It's actually, so you take an ordering of the vertices, and just that ordering of the vertices gives you a min function. Right, so with respect to that ordering, you have two elements. So we get a two-ary function. Between two elements, we just choose the minimum. And if that function is a polymorphism, we call it a min polymorphism. Yeah. Okay. And then the other question, so hopefully I've convinced you that having a nice polymorphism helps solve the CSP problem, or it can. So we ask, what structures have WNU polymorphisms? And, well, this is a hard problem, right? So actually, to decide if a structure has a WNU polymorphism, it is computable, but it's itself NP-complete. So it's a little bit, yeah, it'll be hard to decide. So on my slides, if you want to see what is coming next, you can look on this picture. It doesn't show up. Okay. So as an example, but yeah, for different segments of CSP, we might have nice descriptions. For example, if we only consider targets that are symmetric graphs and symmetric cores, you know exactly what has a WNU polymorphism, because Hal Nesitrel said the H coloring problem for graphs is polynomial only for bipartite graphs, all of whose cores are K2. Right? So the only core with a WNU is K2, and all other cores omit these polymorphisms. So I might ask, which non-cores? Right? So why do we care about non-cores? As I said, I forgot to explain it. For the retraction problem, if I had this graph and I put different color circles around those guys for the retraction problem, when I put these circles around, well, there are no homomorphisms of this to itself except the identity, because this yellow circle can't go to a blue circle. So putting these unary relations there makes this a core. And so we care about this for the retraction problem. But we don't know. Well, we don't know the dichotomy class. We don't have, right. So, right, we don't have a nice description of the non-cores which have WNU, for which the retraction problem is polynomial time solvable. There are some other, here's, right, for digraphs, we know for smooth digraphs, so these are digraphs that don't have any sinks or sources, we know that such a digraph has a WNU if and only if it's a directed cycle. Maybe if and only if it retracts to a directed cycle, sorry. And otherwise, it's NP-complete. So for digraphs, we don't even know for the trees. So we don't have a characterization of which digraph trees have WNU. There's various other dichotomies. Right? Right? So these are all complexity dichotomies. Schaefer gave a dichotomy of which relational structures with two vertices have polynomial time solvable CSP problems. So those are exactly the ones that have WNUs. Okay, so, but he gave a nice description of them. It's just long, so I didn't write it out. Bolatov he proved the dichotomy for Lishom, so he gave sort of a nice description. We'll talk about his result in a second in a bit more detail. And there's various other nice dichotomies, and one of those other nice CSP dichotomies is the switch-Hom dichotomy that we talked about before. Now, if you're really on top of things, you might ask, or you might say, you might accuse, you might yell out at me, switch-Hom isn't a CSP. Because how do I switch? Right? Switch-Hom isn't a CSP. But, right, so Brewster and Graves showed it is kind of a CSP. So if we think about doing a switch homomorphism to this graph, and so think about mapping some so we claim that doing a switch homomorphism to this graph is the same as just doing a homomorphism to this graph. Right, so here's a copy of that graph there. And so we can think of mapping to this. And if I want to switch before I map to this vertex, well, then I'm just going to map to this vertex instead. So that's essentially doing the switch before I map there. Right? So with this they showed that with this reduction, yeah, switch homomorphism actually is a CSP. Okay, so we have a dichotomy because we have dichotomy for CSP. Right. Well, what about the list case? Well, there's a little bit of a problem here because now these two problems are the same. Switch Hom to this or Hom to this. But so that's not working. So if I want to sort of designate a list here that some vertex has to map to, well, then I can map to either of these vertices. Right? If I want to designate this list, then I can map to these. But I can't make this list. Right? So when this is the list version of this isn't quite the list version of this. It is a list version, but I'm not allowed all lists. Right? So the weak near unanimity polymorphism I have on this to make it polynomial is not completely, it doesn't preserve every list. So I could take these three guys and they could map to this. Right? So my weak near unanimity function doesn't have to be completely conservative. We say it's semi-conservative if it preserves just these symmetric lists. And so we get from the CSP dichotomy that the list switch homomorphism problem, which we're calling this, is in P if and only if this thing, which we call the switch graph. And so obviously if we're calling it the switch graph, I denote it P of H. Right? I guess it could have been S of H or SW of H. But only if and only if this has a semi-conservative WNU polymorphism. Right? Yeah.
Is there a homomorphism from the graph from P of H to H? Just a regular homomorphism?
No. In general, not.
Is there a switch homomorphism? I'm just trying to think.
Maybe.
Because why should it be equivalent to? Because maybe you have a homomorphism which is all of the vertices here. Then why should it be equivalent to switch homomorphism to H?
I don't know.
Okay.
No, it's actually the proof isn't too hard that these are equivalent, right? So it's Brewster and Graves did it, but it was a simple couple lines, just looking through the definition. Okay, so right. Okay, so this is the problem we're interested in now. So we're interested in finding for BR graphs 14 out of 31. Okay, well, it's working. If this switch graph has a semi-conservative WNU polymorphism. Okay, and so there's a lot known about list homomorphism. We're not exactly a list homomorphism problem here, but we're very close to it. And so we're going to borrow some tools from what's known about list homomorphism, so we should know those tools. I state this theorem. We're not really going to use this, but it's an important theorem. So we mentioned it before. So Bulatov, before the CSP dichotomy was proved in 2017, so about 14 years before, Bulatov proved it for list homomorphism, right, for conservative targets. Right? These targets that have all the unary relations. So he showed the dichotomy in this case for conservative relational structures, and so we didn't know that we suspected, but we didn't know at that time that the polynomial cases were characterized by the existence of a weak near unanimity polymorphism. So he showed that they have a polymorphism that, well, for each pair of vertices, there's a polymorphism on the graph that is majority. So this is 3NU. That's another word for 3NU, or semilattice or Maltsev on that pair of vertices. Okay. And it turns out this is actually a weak near unanimity polymorphism. This gives a weak unanimity, a WNU. It gives a WNU, and so he proved the dichotomy, and in 2015, it was shown that his condition here was recognizable in polynomial time. Right? So it's a nice characterization in that it's polynomial time recognizable, whereas WNU in general is not polynomial time recognizable. Okay, but, right. But again, it's for general structures, and we would, this tells us then that maybe we'll get nice characterizations, but it's hard to give a nice non-algebraic characterization for structures in general. But for graph-like structures, it's reasonable to assume we might get nice characterizations of the easy targets. And so we actually have some, right? So Feder and Hell in '98 showed that for a reflexive graph H, the list homomorphism problem to H is in P if and only if this H is an interval graph. And so I have various characterizations. So here's a structural characterization. Here's an omitted subgraph characterization. So this was known then that interval graphs are exactly the graphs that have no asteroidal triples. I don't want to explain what an asteroidal triple is because I think they're ugly. And yeah, they're also characterized by the existence of a min homomorphism. Min ordering, min homomorphism. Okay, then a year later, with Huang, they did the same thing for, what is a reflexive graph? Every vertex has a loop. So they did the same thing the next year for irreflexive graphs. Now, these are ugly, but for an irreflexive graph, so this is just a graph for most people, we know that the homomorphism problem is only easy if it's bipartite. So the list hom problem can only be easy when we're bipartite. So these have to be bipartite. And so they characterize the easy bipartite graphs as those that are complements of a circular arc graph. Right? So a circular arc graph is a generalization of an interval graph where your intervals are around a circle. However, this is the complement, not the interval. But okay, they gave a characterization though, a structural characterization, and they had an omitted subgraph characterization, which is kind of a bipartite version of asteroidal triples, but is also ugly. But polynomial time decidable, right? So that's important in these characterizations. We can decide them in polynomial time. So there's different levels of niceness. Somehow, to me, interval is very nice, and min is very nice. These are, well, they're necessary to get those, but they're less nice to me. Okay, and then a couple years later, they generalized to graphs, and it's an interesting result because they showed that for a general graph, so now vertices can have loops or not loops. We can have some loops, right? The problem is polynomial time solvable if and only if, when taking its product with K2, which makes it bipartite, kills all loops, the irreflexive graph we get is polynomial times solvable. And when they did this, they showed that this was characterized by 3 NU polymorphisms. Right? So we know that these are all characterized by WNU polymorphisms. So these are kind of interesting things because they're saying that in the context of graphs, if I have a WNU polymorphism, I have a stronger one. I have the 3NU polymorphism. Right? So it's a collapse of this polymorphism map that we do. And so these are quite interesting characterizations in that sense. Okay, but to me, these things are still ugly. For digraphs, well, actually before digraph, then Bulatov did his thing in general that told us then. Well, we had this sort of ugly description of a WNU here that describes those. So that applies to all these, but so for graphs, that's exactly it gives 3NU. And then for digraphs, Feder, Huang, and Raphael, they did it for reflexive digraphs, and then Helen Raphael finished it for digraphs in general. They gave a characterization of the digraphs for which Listhon is polynomial time solvable. So for which there is this conservative WNU polymorphism. And so they had an omitted subgraph characterization of digraph asteroidal triples, another nasty thing. And, well, Bulatov's polymorphism, but he can remove the Maltsev bit, so it's a little less nasty than Bulatov's. So when they did this in 2012, Bulatov's description wasn't known to be decidable in polynomial time yet. So they showed that it was decidable in polynomial time in this setting. And then we know from about 2015 they all are. Okay. So things that are important here are this reduction. So this reduction from the graph case to the irreflexive case, we'll come back to that. And these notions of a collapse will come back to. And then there's one more paper, more recent paper. Oh, I didn't put it down. So this is by Feder, no, not Feder, Hell, Huang, Raphael, and McDonnell in 2018. It's, do I have? Oh, okay, I do have it. Ooh. Okay, in 2018. Oh, what was that last slide then? Oh yeah, okay. In here, it wasn't so interesting in this paper because these, for digraphs, the easy things are not characterized by 3NU. But in this paper, they found a nice omitting subgraph that characterizes the existence of a 3NU. Right? And so the definitions of the 3NU here, they knew it existed, but they didn't have it explicitly. But with this new omitted subgraph characterization, they get an explicit 3NU. And why this is interesting to me is, well, this was actually Siobin's master's thesis. We did this, and then we found out later it was hidden in this digraph paper. So everything her master's thesis was already done in this paper here. A big part of her master's thesis was already in there. But we use these, so we're also going to use these in a second. And then finally, we have one more characterization here. So more recently, bipartite graphs, graphs without loops, unless they're empty, they can't have a min homomorphism. It's not too hard to show that. But there's a sort of a bipartite version of a min homomorphism where you have a min ordering on each of the bipartite classes. But so anyways, they showed that the easy cases are also characterized by the existence of that. And we'll use that in a second. Okay, so here's it's a lot of stuff I threw at you. We won't use all this, but there's a couple things here that we will use. So let's move on. So what were we talking about? We want to decide for which graphs PH has a conservative WNU polymorphism. And so the first step was, well, we said, well, which ones have a conservative WNU polymorphism? Forget this semi-conservative, which ones have conservative? Right, so we're actually doing the list homomorphism problem on the switch graph. And for that, we get a pretty easy, a pretty nice characterization. So we say that, right, so for a BR graph, this homomorphism problem for the switch graph is in P if and only if, well, we have from the CSP dichotomy is if and only if the switch graph has a conservative WNU. And so if it has a conservative WNU, that WNU conserves red edges and blue edges. So certainly the red subgraph has a conservative WNU. And from Federer-Huang, we know that if the red subgraph, it's just a graph. If it has a WNU, well, then it has a 3NU polymorphism. So what we had to do is show that that 3NU polymorphism on the red subgraph of the switch graph actually preserves the blue edges as well. Right, so this is all we had to do, and then we got, right, if we can show that, then we get that PH, the switch graph, has a conservative 3NU polymorphism, which is a conservative WNU, a strong conservative WNU polymorphism. So it gives this nice collapse from WNU down to 3NU for these switch graphs as well. And so I want to, I guess, okay, so I'll go through some of the ideas of the proof of this. Oh, when are we stopping? Okay, so there's some simple, nice ideas. So first I want to start with showing you how I can show a graph like this, which doesn't have a conservative 3NU polymorphism, how I can show it doesn't have a conservative 3NU polymorphism. Right? So I assume it does. So I look at where this 3-tuple will map. This 3-tuple, because it's conservative, it has to map to one of those vertices. Right? So I assume it maps there. Well, then this adjacent 3-tuple has to map there. Right? It has to map to one of those vertices, but only this one was adjacent to that one. And then this adjacent 3-tuple has to map to the top there. And finally, this adjacent 3-tuple has to map here, but I have 2 of my entries are here. And so that's not majority. That's not a 3NU polymorphism. So that's how we can show that doesn't exist. Well, so what they did with these permutable triples is they said, essentially, if we find this in our graph, then for the tuple ABC, it can't map to B. Right? So these are, this is a path and this is a path with non-edges there. So if I have this structure in my graph for A, B, and C, my polymorphism can't map to B. So if I have a similar structure with B in the middle in one of the structures, A in the middle in the other structure, and C in the middle in the other structure, then I can't have a KNU polymorphism. Right? So I call this a B excluder. And if we have all these A excluder, B excluder, and C excluder for ABC, we call that a permutable triple. And so from, this was Helen Raffier, they showed that permutable triples omit conservative 3NU. And then they showed if H has no permutable triples, then we can define a 3NU polymorphism in this way. So they just say, where do these 3 vertices have to go? Well, if 2 of them are the same, we have to map to that target. And otherwise, I'm just going to choose the minimum index that has, for which there's no excluder. There's not one of these B excluders with that vertex in the middle. Right? So that's not too hard to show. It takes about a page or 2 to show that, but it's a pretty quick proof. And so what did we do? We said, well, if we define it this way, a definition like this is preserved under automorphisms, right? The existence of these excluders is preserved under taking automorphisms of the target. Which index we choose doesn't matter when we take an automorphism of the target, and majority is preserved under taking automorphism of the target. It has nothing to do with the target, right? It has to do with the entries. So this polymorphism commutes with automorphisms of H, and in particular, it commutes with the automorphism that switches the 2 sides of that switch graph. And so because it commutes with that, well, when we do that switch, it switches red edges with blue edges. And so because it preserves red edges, it also preserves blue edges. And so because we can define the 3NU with this that commutes with automorphisms, it actually also preserves red edges. So that's all there was to that proof. Okay, but what we're really interested in is semi-conservative WNUs. And so we had hoped that a graph that has a semi-conservative WNU also has a conservative NU. But that turned out not to be true. So we were hoping we had this collapse. It turned out not to be true. Too bad. And then so Pavel suggested, well, because they have for graphs, they have a collapse from WNU to 3NU. Maybe we have that, right? But no, that turns out not to be true either. So we can't say that a graph, so there are graphs with semi-conservative WNUs that don't have semi-conservative 3NUs. So sort of the easy routes to proof have disappeared. They don't work. So that means there's a lot of work left to do. But luckily, there's a lot of work done. So Bach, Brewster, Feder, Hell, and Jedlikova, they actually characterized the trees, the red-blue trees, for which the list home problem is polynomial time solvable. Right, so I'm going to explain the characterization for irreflexive graphs. Right, okay, so here's the characterization for irreflexive graphs. So they say an irreflexive blue-red graph H, switch hom is in P if and only if it has what's called a special bipartite min ordering, and if and only if the graph is a good caterpillar. So I'll describe this first. So a good caterpillar is what? Well, they start with a path, and so, and on that path we have purple edges until a certain point, and then we have red edges. Now, these could be blue edges, but we can switch them to red. It's not too hard to see. So we can assume that everything's purple and red. Right, so they start with that, and then at each vertex in this path, we're allowed to have a tree of depth 2, of depth up to 2. Right? And we can remove the blue edges from some of the leaves. There. And the trees here, they have to be red. So basically, here's a description of a good caterpillar. So it's this, it's got a spine, it's got trees of depth at most 2 from each vertex. The ones off these purple vertices can have purple, and then we can remove blue edges from leaf vertices, right? And so this is exactly a description. So what is a special bipartite min ordering? So a special bipartite min ordering is a bipartite min ordering, which is much like a min ordering. I'm not going to describe it yet. We'll see it in a second, maybe. Of the underlying graph with this added property that for every vertex, its red neighbors are above its purple neighbors. Maybe I should have switched these, but we can see that that holds here. Right? And so they showed that this characterizes the irreflexive trees for which the list switch hom problem is polynomial. And so they have similar characterizations for reflexive trees and general trees. This takes 2 or 3 pages. This one takes about 12 pages, so it gets a little bit ugly. The descriptions get a bit uglier. But so the good caterpillar descriptions are similar. And then here they have a min ordering, a special min ordering, and here they have to do something else. So things get a lot uglier. Okay, so this is what they did. And then, right. Okay, so now what do we do? They gave us a lot of examples, so they really let us understand the problem a lot more because they gave us a lot of examples of things for which the switch hom problem is polynomial that we didn't know about. Right. And so now we made this observation. So for in a reflexive graph H, if the list switch hom problem is in P, then we can assume, as they do for trees, but we're doing this in general, the red subgraph has a min ordering. Right? So we observe we can do that. and that we can switch the graph to be only red and purple, so there's no purely blue edges. And so here's sort of the idea is why we can do that, but it's just using a lot of old results, putting them together to make this statement. But so the reason this is nice is then maybe close to a characterization of the guys for which the problem is polynomial time solvable. Because if it's polynomial time solvable, I take a graph. How do I get a graph for which the switch-Hom problem is polynomial time solvable? I start with a graph, a purple graph with a min bipartite ordering, and then I just remove some of the blue edges. So I really just have to decide which blue edges I can remove from these purple graphs. Right? And so at first we thought, well, let's just remove blue edges that don't break the min ordering. Seems a good way to start. But actually their result said, well, that's not enough. Right? So when we see their result, we say, okay, a bit stronger. Let's look just at special bipartite min orderings. So I have a min ordering on a purple graph, and I can remove blue edges as long as when I remove a blue edge, that leaves a red neighbor, that has to be above any purple neighbor. So I have to remove, for some vertex, if I remove a blue edge, I have to remove blue edges to any neighbor above that edge. So this is what we conjecture. It's a temporary conjecture because we don't have a lot of evidence for it. What is our evidence? Well, it's true for trees. And it would be nice. So this is why it's a temporary conjecture because, well, we're not so confident on it. But it gives us a goal to shoot for, right? And so towards that goal, what can we do? Well, we start, instead of starting with a tree, a purple tree, we start with a purple bipartite interval graph, right? So we take some graph that has this min ordering, and we know what they look like. And we say, well, what can we remove? We try to show what we can remove. Well, I know I can pick some vertex and remove everything above, all the blue edges above that. I can deal with that. I can, down here, I can also remove edges adjacent to leaves, right? So already we've done what they do in the tree case. But also I want to add this. I want to remove what I call leaf edges dependent C4s. Right? So here's a C4 where two of the vertices have degree 2. I'm going to remove the edge between those vertices with C2. Now if these are in distinct C4s, then I can show when I remove these kind of edges, then pH has a semi-conservative WNU polymorphism. Right? So Bach, Brewster, Federhell, and Yedlikova, they didn't give the explicit WNU polymorphism. They used sort of this min ordering consistency check algorithm to show that they were polynomial. We find the WNU polymorphism. And further, we find a WNU polymorphism. So we're defining it not on the tree, but on the switch graph of this tree. And we define it so that it commutes with this switch homomorphism again, which is unnecessary, but it's useful because, well, remember that Federhell and Huang had this reduction to the bipartite case. Okay, let's go a little bit fast. So when they proved this in 2002, it took a lot of work. But there's a lot of tools now, which makes this quite easy. So the basic idea is, right, so what did they show? They showed that list hom for this is easy, if and only if list hom for this is easy. Right? And so how would I show this now? I would say, well, this is bipartite, so the kth power of it is disconnected. So what does that mean? That means if I'm trying to define a homomorphism on it, a polymorphism on it, right? So I have a triple here. I have to decide where it goes. And wherever it goes, that gives constraints to where other triples can map, right? But the other triples that are constrained, so this one, I call this, say it has constant parity because all these vertices are on one side. Well, the only neighbors are also constant parity, right? So the only sort of neighbor triples have constant parity also. And so when I define it on this constant parity triple, it only adds restraints to other constant parity triples. Right? So the power is disconnected. And so I can actually define a polymorphism on here on these constant parity triples if I have a polymorphism here in the following way. Well, those edges map to edges here, right? Because this is what I've done. I've taken the product with K2. So those edges go to edges here. And if I have a 3NU polymorphism here, that tells me where this triple goes. It goes here, and this triple has to go here, so they come back to an edge, right? So if I have a 3NU polymorphism here, I get one on the constant parity triples here. But on the other triples, it's easy to define them because I just have to take a projection. So if H has a 3NU, then H times K2 has a 3NU, and it has, well, a parity symmetric 3NU. Right. So, right. So we could prove this Federer-Helfwang result pretty easily now, and we can generalize it. So it certainly works for red-blue graphs. And so what we get here is this sort of technical lemma that says, if I have a polymorphism on H, I have a parity symmetric polymorphism on H times K2. This is actually if and only if. Right? And if that polymorphism is conservative, this one is conservative. If it's 3NU, this one's 3NU. If it's WNU, this is WNU. If this is min, well, this is a bipartite min ordering. And if it's semi-conservative, this is semi-conservative. So all at once, I get that if, oh, yeah. And so finally, all at once, I get if the switch-Hom problem is polynomial for H, then it's polynomial for this. And I can go the other way if the WNU I've defined is parity symmetric, right? Okay, and so, right. So then, what do I do? Right, so let's take some graph, and I want to show, right, so I want to go the other, I want to go in the other direction. So say this has a semi-conservative WNU, and say that this has these special ones that we've defined that sort of extend to the switch graph with this switch symmetry. Then so I have some bipartite graph here that it has the right polymorphism. It has this bipartite min ordering. And I take that and we can actually show that if a bipartite graph has this bipartite min ordering, it actually has a symmetric one, right? So symmetric with respect to this automorphism through here. And then when I take the product, the switch graph of that, because that weak, the semi-conservative WNU that I defined was switch symmetric, it commutes with this automorphism here. And putting those, since it commutes with both of those automorphisms, it actually commutes with this as well, just commuting with it both. So in the end, we get a switch WNU polymorphism on the whole graph, on the switch graph of H times K2. Well, H times K2, but H times K2 is the same as the switch graph of H times K2. Right? It's not too hard to show. And so then we can say, well, we have the nice polymorphism on here, and it's symmetric. And so it gives WNU on the switch graph of H. Okay, so I got a little bit mixed up in that, so I went a bit fast, and clearly no one could have followed that. But what is the kicker? So what do we get from that? So what we get is that, so if we can extend our result, so our result, we haven't proved it for all graphs. We've proved it for more than trees, right? we've shown that if these graphs that sort of fit our description, if the list switch problem is polynomial time solvable, then we can define this WNU, the semi-conservative WNU on this switch graph. And since we defined it to be switch symmetric, we can use that result to give the same result not only for irreflexive graphs, we can give it for any graph whose product is that irreflexive graph. Right? So if we can sort of finish our result for irreflexive graphs in the right way with this right symmetry, then we will actually we'll get the whole characterization for all graphs. And in particular, so a lot of the stuff from the Bach, Brewster, Federer, Hell, Jedlikova paper, we can do very quickly by this reduction now. So we certainly don't get the characterization. So a lot of their work is actually showing that if they don't fit the description, then the problem is hard. And we don't get that. But we do get the proofs that the things are, we get the P side proofs of their result for free just from the irreflexive case. Okay, so I stop there then.
Thank you. Any questions?
I have a question.
Yeah.
What if we use specific colors instead of red or blue and use some color prediction in a cyclic order instead of switch?
I think it'll get a lot harder. But yeah, so certainly we can consider this. So actually, even the dichotomy for two-colored graphs, we don't even know. So like throwing away this idea of switching, we don't know. I think if you, it feels to me like it's a much harder problem. Certainly, yeah. I haven't considered it. It's a nice thing to consider. Right. To me, it seems interesting. Right. So I always fight with the problem. It seems like an interesting problem. See what you can do with it, and then try to motivate it. Right. So the motivation comes last. So with a problem like that, I think, yeah, okay, that seems interesting. We have all these papers about signed graphs to somehow motivate this. Of course, I didn't talk about signed graphs, right? So I didn't talk about that motivation. What's the motivation there? Because it's a nice problem. Yeah, okay, it's a nice problem. So we can consider that. But we certainly haven't thought about it at all.
Many years ago, when I attend the health talk, we always motivate these problems as such that because we don't know the dichotomy conjecture is true or not for CSP, so here's one instance where we know the conjecture is verified.
Yeah.
Now
and then Bulatov and Zook went and proved it, and we have nothing to work on.
Yeah, so
exactly. So motivation becomes more difficult. But yeah, the point is we still don't know the characterizations, right? So a lot of times it's to actually decide for which graphs it's easy. That's an NP-complete problem on its own. So we're not going to get a good characterization. But certainly for these list ones, we have a chance of getting a nice characterization.
Some like variation of these problems where it cannot be encoded as a CSP, and yet we wish to have dichotomy between P and complete.
Yeah, I think so. Certainly, I mean, the switch home one, actually, you're right. So it wasn't a CSP. We encoded it in CSP. So are there, yeah, okay, so this is the question. Yeah, this question comes to people that do logic theory talk about this. So if P and MP complete are different, there's intermediate complexities, right? And so people are saying, what level of logic is necessary to find, to get problems in that complexity? And so this showed we're not going to get it with CSP. So then people ask, well, okay, if we enrich CSP, and probably you know better than me what the next right? So if we, right, so these are CSP are basically, so we have relations, and then we can define things with primitive positive formulas in those relations. So you have to allow a little bit more, right, quantification over subsets or something like that to, you can sort of get more expressivity, and people talk about the complexity of those. So I don't know what exactly we need to be able to get these intermediate, well, we didn't know if we could get these intermediate problems with CSP, and we've proved we can't now, but yeah, people consider this. Yeah, what do we need to get the intermediate?
Is there any nice parameter to investigate parameterized complexity of the problem?
One more time?
Is there any nice parameter to investigate the parameterized complexity of the problem? Maybe it's homomorphism switch. I don't know.
So in a way, CSP, when we talk about CSP, we sort of first say the problem of deciding if there's a homomorphism between two structures. We show that that's MT complete. And then we parameterize it by fixing the target. So in a way, it's already, there is already a parameterization in terms of the target. Right, so there's these things, CSP problems are, we know that they're polynomial time for bounded tree width, say. Right, so you could parameterize the complex, so then we can look at sort of fine-grained complexity in terms of parameters, in terms of, tree width, or basically any of these things that make the problems polynomial. We can look at the complexity in terms of those parameters. Is that maybe the kind of thing you were asking? Yeah, but I don't know much about that.
I was curious about this from this perspective is, so for sine graphs, people usually consider this matrix coming from the sine graphs, like a list of cycles, balanced cycles form a vector space, and then you can think of the like these cycles,
Right.
and then you can still think of the homomorphism between these vector spaces, mapping collection of vectors to whose sum is zero, whose some linear combination is zero, to another collection of vectors whose linear combination is zero.
Okay.
So cycles to cycles.
Right.
And you can say, oh, that's maybe homomorphism between.
So a map
Maybe.
between matroids
Yeah.
is a homomorphism if it
Right.
takes
And
cycles to
then
cycles.
I was wondering whether some characterization of homomorphism between this matroid could give something over here, but anyone or any potential directions? Matroid doesn't.
I've seen the definition of matroids.
Alright.
I've seen a couple of the definitions. Yeah. I'm not sure.
Any other questions? So if not, let's thank the speakers.